Greetings, welcome to iste780 Data-Driven Knowledge Discovery, Day 17. In some ways, perhaps the most interesting day since we're going to be talking about support vector machines. Also, I'm trying to do things a little bit differently today, so I hope you like that. Now, let's get started. What you're looking at is a hyperplane, and that may raise the question to you, what is a hyperplane? And it may also raise the question to you, what is it in this picture that I'm looking at that is a hyperplane? And indeed, the hyperplane is the heavy black line going from upper left, diagonal line going from upper left to lower right in this picture. And this particular hyperplane is a line because it is in two-dimensional space, and the textbook definition of a hyperplane is, in a p-dimensional space, a hyperplane is a flat affine subspace of dimension p minus 1. And what you see here is a picture of dimension p equals 2. So p minus 1 would be 1. So p minus 1 would be one dimension, a subspace of one dimension. A subspace of one dimension would be a line or a line segment. And a hyperplane can, in p minus 1 dimensions, can separate a p-dimensional space. And that's indeed what's happening here. This line, this diagonal line, is separating this space into two parts. The part that the textbook calls the purple part, which looks pink to me, but anyway, well, I'll call it the purple part, I guess. And the part that the textbook calls the blue part, which actually does look blue to me. So in any space, any p-dimensional space, a hyperplane of dimension p minus 1 can separate that space. Now that should suggest to you that it's useful potentially as a classifier, since any points in the purple space lie on one side of the hyperplane and any points in the blue space lie on the other side of the hyperplane. Also, the hyperplane has a nice concise definition, and that definition looks very much like the definitions that we've seen for all kinds of things in the past, in the earlier part of the textbook. And that definition is 1 plus 2x1 plus 3x2 equals 0. So that is simply the equation of a line. And of course, it's something that we are used to using various techniques like least squares to identify that line. Okay, now on the one side of the line, the points are 1 plus 2, the equation, I should say, 1 plus 2x1 plus 3x2 is going to be greater than 0. That is on the blue side. And on the purple side, that equation, if you plug in any of the x1 and x2 values on the other side of that line, the equation will come out to be less than 0. So that's a really good and easy way to classify things if a straight line works for separating all the points. In other words, if all the points are clearly on all one side or the other, that may be a good way to classify those points. In particular, if all the points of one sort are on one side and all the points of the other sort are on the other side, then that's an excellent way, it's an exquisite way to classify. Now we have two classes of observations, the blue observations and the purple observations. And it is possible to draw a line, that is to say a hyperplane. By the way, I think I mentioned in 2 dimensions a hyperplane is a line. Did I mention in 3 dimensions a hyperplane would be a plane? In 4 dimensions it becomes hard to visualize, but it still exists. It's still a construct that's one dimension less than the number of dimensions of the space, and it cuts through the space. In any event, this particular set of points has several different lines. You can see there in the left-hand panel there are 3 different lines that intersect, that all have the blue points on one side and the purple points on the other side. So we can pick one of those and say that this line is the separating hyperplane. But the question is, which one do you pick? Do you pick the one, one that's the most vertical? Do you pick the one that's the most horizontal? Do you pick the one that's that looks like it works the best somehow? Well, in fact, what we'll do is pick one that is actually the one on the right side, which is called the maximal margin classifier. Here's a maximal margin hyperplane, the black diagonal line, along with its support vectors, which are the dots that are indicated with arrows pointing to the hyperplane. And these vectors define the margin. This is the marginal area between the blue space and the purple space. And you may not, if you haven't done much linear algebra, it may not occur to you to think of these points as vectors, but in fact they are. These are each point is a two-component vector. It has an x1 component and an x2 component. So each one of these observations is a vector in P space. And if we draw a perpendicular line from the vectors to the maximal margin hyperplane, we'll find that the best fit is going to be one that makes this margin, the space between the two dotted lines, as large as possible. So this is only going to work, obviously, if all the purple points are some distance away from all the blue points, and that there is some band that we can call the margin that runs through there. And that's not going to be the case in most classification problems, but it illuminates the idea. I think it gives the flavor of what's to come, and kind of gives us an indication of what support vector machines are going to look like. So keep this in mind as a very, very simple example of an idea. Now, and there are a couple of things that you should keep in mind about this idea. One thing that's very cool about this idea is that this maximal margin hyperplane only depends on the points at the margin. So all the other points here could move around as long as they don't get into that marginal area, and it wouldn't make any difference. That's a really great computational advantage, to only have to deal with points that are somewhere near this relatively small region of the margin, relatively small compared to the rest. Here's an example of an optimization problem. And this particular optimization problem is actually the problem that has to be solved to make the picture in our previous, on the previous slide work. In other words, to obtain this maximal margin classifier, we have to solve this problem. And M is the size of the margin. And the two constraints simply ensure that that every observation is on the correct side of the hyperplane, and that every observation is at least a distance of m away from the hyperplane. That's really all that you need to know in this class. So if you took an applied math class, you would learn how to solve this problem yourself. We're simply going to rely on R to solve the problem for us in each case. All we need to know is that this problem is being solved, and that if, again, we have this very special condition that all the points are easily found to be on one or another side of the hyperplane, then a maximal margin can be found. And this is the formulation that will find it, and we'll find it very quickly and easily, even if there are a great many points. Well, typically we are in a situation that looks more like this. So there is no hyperplane, there's no separating hyperplane. There's no way that we can use the maximal margin classifier. So we need something else. What could it be? What could we use? Can we use anything from the idea of the maximal margin classifier in this picture? Think about it for a second. What would you do? Imagine that you only need to deal with the observations that are sort of in question, and that you could forget about ones that are far away from some margin between them. Think about what you could possibly do that would be like the maximal margin classifier, but that might work in this kind of situation. One of the problems that you're going to face if you try to use something from the maximal margin classifier is that points near the boundary have potentially a dramatic effect on the shape of the maximal margin classifier. So notice in this picture we start out with, on the left panel, points that are easily separated, but on the right panel we've simply added one point, and we've had to very, very drastically change the equation of the line that will separate these points. It's still separable, but it's so different, and just because of one observation. So the observations that are far away from the boundary don't seem to make a big difference, or any difference at all, actually, if they're the right classification. But points near the boundary can have a huge influence on the maximal margin classifier. According to our textbook, a way to solve this problem is to find a method that gives greater robustness to individual observations, so it doesn't fluctuate wildly when one observation near the boundary is introduced, and that gives better classification of most of the training observations. And the result is a soft margin classifier called the support vector classifier. And here are a couple of examples of it. In the example on the left, you see that some points have wandered into the margin. So the support vectors here, you could say, are 9 and 2 and perhaps 3. Those points seem to be right on the margin, and those could be the support vectors. But then points 1 and 8 are inside the margin, so that's problematic. That's something that the maximal margin classifier couldn't deal with. In fact, the maximal margin classifier would simply move the dashed lines in to reflect the location of points 1 and 8. So this is a more robust idea to allow some points into that area. And then even further, if we go over to the right-hand panel, you'll see that 12 and 11 now are on the wrong side of the separating hyperplane. So now the situation is even more of a violation of the maximal margin classifier. It simply couldn't represent this at all. It could represent the left-hand panel with a much tinier maximal margin, but it couldn't represent what we see here at all, but the support vector classifier can. Here's the problem that the support vector classifier has to solve. This is another optimization problem, and it looks very much like the optimization problem that we saw before for the maximal margin classifier, except for this one really wonderful constraint, equation 915. And this constraint makes this really different from the maximal margin classifier. This constraint allows what we call slack variables. And you'll notice that there's a slack variable, epsilon sub I, for every observation. So we have I going from 1 to n, so that's all of the observations. So each observation has a slack variable associated with it. And if that slack variable is 0, it means that that observation is in the right place. It's on the right side of the margin. If epsilon sub I is between 0 and 1, it means that it's in that space that we talked about between the margin and the plane. It's not in the right. It's not completely in the right place, but it's not completely in the wrong place. The completely wrong place would be if e sub I is 1, in which case it means that the observation is on the wrong side of the hyperplane itself. So that means it's on the wrong side of the solid line in the previous picture, not on the wrong side of the dashed line. So it's farther into, and we'll call it enemy territory, than it would be if it were between the dashed line and the solid line. So those slack variables are now constrained by C. So that capital C there is a tuning parameter, such as we've used in some of our previous encounters with techniques. And in this tuning parameter, if it equals 0, that means we allow no slack. If C equals 0, it means that every observation, in fact, it basically means we're using the maximal margin classifier. If C equals 0, it's as if this constraint didn't exist, as if we were trying to solve the problem above, and with no slack variables. But if C equals 1, then that means that we've allowed one observation to be on the wrong side of the hyperplane. So the larger that we allow C to be, the more we're allowing to be on the wrong side of the hyperplane. Here's an example of using the tuning parameter C. So here are 4 pictures in which C is decreasing in each picture. So in the first picture, the margin, I should say, not the maximal margin, just the margin is the largest, and it doesn't even fit all into the picture. We can just fit one side of it. Oh, I guess it does fit in. I take it back. You can just see in the very upper left-hand corner, you can see the upper side. So, so that's a very wide margin that allows for a lot of error. So that's with C being very large. The panel next to it, the upper right panel, has a somewhat smaller value of C. The lower left panel has a still smaller value, and the lower right panel has the smallest value of C. So you can see that we've tolerated fewer and fewer violations of the margin as we tighten it by shrinking C. Now here's a problem that the support vector classifier simply can't handle. And the reason is that the support vector classifier is linear. And so if we look at the problem on the left side, try to imagine drawing the best line to separate through it, the best straight line through it, to separate the blue points from the purple points. Very hard to conceive of. And in fact, what you see in the panel on the right-hand side is the best linear boundary that can be found, and it's sure not very good. In fact, it's not acceptable in any way. And it's because of the linearity of the support vector classifier. So guess what we're going to talk about next? So here's a completely different formulation of the maximization problem that we just looked at. And it's primarily different in that it's got a lot of polynomial terms. If you take a look at the first row there, under the word maximize, you'll notice that it's quite different from and potentially quite a bit more than the terms in equations in equation 912. So this is going to allow for nonlinear boundaries, and it's the reformulation here actually is going to look linear, but it's based on a nonlinear source. So it's going to allow, if this can be solved efficiently, it's going to allow us to construct boundaries that are nonlinear. Before we actually look at the solution to the previously displayed maximization problem, let's reformulate how the support vector classifier looks. Now first we need to know a bit of linear algebra notation here. this notation just is the inner product of two vectors. It's shown with these angle brackets. So if we have these vectors, we have an inner product like that. So if we look at the solution to the linear support vector classifier, we can depict it as as a sum of a bunch of inner products. And estimating these, we only need n choose 2 inner products, and n choose 2 is called the binomial coefficient, and it's spelled out as an n over some other, n over k or n over p, something like that. And in this particular case, it's n over 2, and it just means it's equivalent to n times n minus 1 divided by, in this case, 2. So once we have that formulation, we can then play around with it, which we will in the next picture. The support vector machine introduces a concept called a kernel, and this kernel is just some function, and in this particular case you can see two examples of such functions. The first one is a polynomial kernel of degree d, where d is a positive integer, and the second one is a radial kernel that is with gamma, the letter gamma just before the summation sign there, is a positive constant. And I'd like to just show you pictures of these two kernels in action. And in a way, this is the climax of today's pictures. So here is the situation we looked at previously that the linear support vector machine couldn't deal with. And here are two different, the linear support vector classifier couldn't deal with. Here are two examples of support vector machines which are nonlinear, both of which can accommodate this. And these are the two kernels that were seen on the previous slide. And as with the other techniques, you don't have to learn how to create these. You simply have to learn how to use them, which we'll do tomorrow in R. Finally, let's take a look at some performance data. Here are ROC curves for the heart data training set, and in this case, and by the way, I should say again, because we haven't looked at ROC curves in a while, what you want is for them to hug the upper left corner. So you can see that the support vector machine performs slightly better than LDA. That's linear discriminant analysis in this case. And and gamma is essentially the tuning parameter here. So we see in the right panel different values of gamma. Now there's another figure in the textbook showing this on the test data set. So this was the training data set, and there's one for the test data set, which also shows a very, very slight improvement of the support vector machine over LDA, but not really significant. This is the most flexible technique that we've covered, and the least interpretable, and a popular one. And I hope that you enjoy working with it tomorrow in the lab. Thanks for your attention. Till tomorrow.